Nothing now.
Welcome, good morning and good afternoon to our webinar for lab products and their application. Discover the benefits of laboratory instruments. My name is Peter Raser and I'm hosting you today through this webinar. I welcome my colleagues, Todd Jordan, business application experts in Americas, and Manfred Seiler, market manager for lab products, sitting in Germany with his 25 years experience in and around all the lab business. Within the next 45 minutes, they will bring you through the topics. And before we hand it over, just let me remark 2 technical comments. You can always place questions into the webinar's Q&A chat. We will collect them, and in the end, we sort them out and do our best to answer all of them. By adding your name, you make it easier for us, if we cannot answer a question directly, to follow up with you later on. So by that, let's start with some content, not losing time. Therefore, you can see here a rough overview of what we want to go through today. And we want to start with the slogan, if you can measure it, you can control it. For that, we will look into charge in the laboratory measurements, the PCD06, the SFP10, what means dissolved in fiber charge, how charge is measured, what is the two-charge strategy, round it up with drainage, freeness, and retention on our DFR05 device, and giving you some demonstration how these units work. By that, I hand it over to you, Todd, and wish you fun to go through the content here. Thanks.
Wonderful. Thank you, Peter. We're going to spend this part of the hour talking about these devices. And we start out with this statement: if you can measure it, you can control it. And the reason that we're having this webinar is this is bringing information into view that you can use. And once you have it, you can use it. You can take advantage of it. It can help you make decisions. Without it, you're kind of guessing. You're taking big risks by adjusting things without that information. But the information is available and we can measure it. It's a complicated world out there in paper making. We've got things going on. We've got people doing a lot of things every day, making decisions, generating a manufactured product. Paper's turning up on the reel. We want it to have a certain quality. We need to run it at a certain production rate to pay all the bills. And more, the material we're making the paper out of is being challenged. For the last 20 or 30 years, there's been a lot of development of chemistry that's going in to help aid the process operation and provide function to the end paper, a functional additive. And the outcome of those chemical additions, the quality of the paper and the efficiency of the paper machine are really dependent on how those additives interact in the system when you first put them in, when they first get in the paper, and over time as you go. And when you put these materials in water, you start developing slight charge, and electrical attraction or repulsion tends to be the primary driver of a lot of these interactions. And each one of the components that you're using, from the raw material you're sourcing to the water you're bringing in or recirculating, or the additive you're putting in there, has characteristics that really impact and can drive both the efficacy of the additive and the efficiency of all the things that are being put in there for your dollars that are being spent. So with that background, what's going on today? Well, when you're putting in functional additives, you're trying to get a quality spec. You're trying to meet a spec. You're trying to give the paper a property, wet strength, sizing, brightness. And when you have a spec, you tend to add a little more than you need. You're moving just past the guardrail to get what the results you desire with that additive. Now, if you don't know where the guardrail is and you don't know exactly how far past you are, it's tough to know exactly how much you're overusing. But in most cases, with rough estimates, it's probably somewhere in the neighborhood of $1 million to €1 million in overuse just by targeting without information of where you should operate. Now, A little bit is good, and more is better kind of creeps into human nature. And sometimes we go even past that point of overdosing for quality because we think a little more might help a little more. In reality, it hurts. It can affect the paper quality negatively. You can run into issues with poor quality, and then you get into deposits. You can get into process problems like foam, and you can get into breaks, downtime, and rejected paper for those reasons. So there's a lot of penalty for not having information in the area that we're talking about. And the benefit here is we're going to add information and shine some light on the process that lets us make adjustments to deal with these areas. So you may be thinking to yourself, gosh, this sounds bad. Am I having that problem and I'm not aware of it? Well, sometimes you're aware of it, sometimes not. So relevant questions that you might want to consider as we're going through this today are, am I sure that the dosage points of my additives are optimized? Am I in the right place? Am I in the right order? Lots of trials are run. If you walk through the basement of any paper mill, there's red rubber hose running everywhere. And there's a lot of attempts to get these things correct. But years go by, things get changed, things are being added to places that were 2 generations of engineers earlier, and you're never quite sure, are we still doing the right things? If you're adding more waste paper or ash has gone up, maybe that's changed dramatically. Great question to ask yourself. The second question is a really good one because you really want your additives on the fiber so they go into the reel and do what they're supposed to do. Do you know they're getting in there? Well, to some effect, yeah, you've got a quality spec, but how much is getting on there? Am I getting a good return for my dollar from what I'm putting in there? Great question. What's my operating window when it comes to charge? There's an operational window of good and bad, and being in the window, kind of being on the road, not up against either guardrail, is possible in every site. How are your facilities doing in that world? Great question. The last one is one that's really interesting with the pursuit of new grease-resistant technology without fluorochemistry, lighter weight sheets of paper. We're looking at combining additives, moving to surface treatments, bringing things back into the wet end. Can we predict the performance or the impact of these additives in the lab before we take them out to the manufacturing line and use them in the full scale? That's a great question to ask. And we've got some good news for you here today if that's a question you've been asking, because the old way of doing it was difficult. The new way, it's a lot easier to get the result. The bottom 3, if you're experiencing these things, these are things you might see every day. You're in your morning meeting and people are talking about increase in dosages, dealing with foam or deposits, outbreaks, stickies, etc., issues with drainage, having failed release from formers, having high moistures. If those things are going on, it's quite possible your process is telling you you might need a little more information in this area. So if any of these things resonate with you, you're in luck. We're going to spend the next few minutes talking about how to get more information that can answer some of these questions and certainly address the things that are seen on the bottom that are almost certainly costing you in production and dollars. We're going to introduce you to the lab portfolio. There are 3 devices here that you're going to hear about today, and we're going to start on the left. And if you look at that device, it's the particle charge detector, the PCD06. That sounds very scientific and specific. But if you look real closely on the front of the device, you'll see the word MUTEC. And if you've been in the industry as long as I have, you've been around a wet end lab that has a MUTEC in it. Hey, what is the MUTEC telling us? Have you run any MUTECs? Same device, newer generation. We're creating wonderful information on the process that's kind of the Kleenex of the industry. It's a device that people know and love, and there's easier ways to get that information faster with some of the latest developments. So we're going to talk about the MUTEC, the particle charge detector today, and what it's doing to bring information to your hands to make decisions. In the middle, we're going to talk about system zeta potential, benchtop measurement that provides a different but highly valuable insight into what's going on in the wet end and the forming section of your machine. Fantastic information. We're going to talk to you not only about how it's making its information known, but how to use it together with the MUTEC, the PCD, to get a really good understanding of the process. And then on the right, the drainage freeness retention module is going to be a way to predict performance on the machine that replaces some older, cumbersome, effective ways of getting predictive modeling that has gone away. You go look around for a Brit jar in a lab and you won't find it, or maybe it's a box somewhere else. This does the same type of information output way faster, way more reliably, and most of it's automated. It's a fantastic device that we want to educate everybody on, because I think there is a benefit there to create information to help you choose a path forward. So with that being said, let's get into these devices. So, electric charge. We talked about measuring charge and looking at system charge and electrical interactions. These two devices are the ones that are going to really shine the light into your process that allows you to understand what's happening and answer a few of those questions that you're looking at, like, what's my charge window? Am I getting on the fibers? But in order to do that, we need to introduce what each one of these devices is doing and how they tell their part of that story. So we're going to start with the good old MUTEC, the particle charge detector. It's looking at information that's in the water phase, dissolved stuff in your water. And in the 80s and beyond, alkaline conversions, different sizing was being introduced. Paper recycling was starting to come back. The paper chemical world was starting to look at all kinds of interesting new things to give functional properties to paper, inkjet printing, waterproof labels, and all kinds of repulpable yet durable produce type boxes. We had all kinds of things being introduced to the wet end of a paper machine, and you can see a lot of work was done to bring the MUTEC, the PCD, along for the ride. The key thing to remember here is this is looking at the water phase. When you take a sample, you're separating the fiber out to see what's going on that's dissolved in the water. It's really good at seeing if there's excess fiber additives that have made it into the water and being overdosed. It's very good at looking at the effectiveness of those chemical reactions. But the key thing to remember, water phase measurement. It's going to help us understand what's floating around and working with the solids that are dissolved in your water stream, which makes up anywhere from 96 to 99.5% of your wet end water loop. That's why this measurement has become the dominant one in the industry to understand what's going on, is because water is the thing. So now we know the PCD, the MUTEC, and its role and the measurement it's making. The other device, the system zeta potential, has been around not quite as long and not quite as many iterations, but it was discovered that similar types of measurements could be made across a fiber mat to give us good information about the fiber's ability to absorb additives, the actual charge on the surface of the fibers. And that was a really interesting way to understand the process. If chemicals ended up in the water, that's a scary thing. But we also want to be able to tell if they're getting onto the fiber. Are they using up some of that footprint of the fiber charge that's available? This device allows us to do that. It can tell us, are changes being seen from an additive being put in the system relative to the fiber? So we have a charge that looks at the water phase, and now we have a charge that looks at the fiber phase. And we can start to look at how they're making their measurements, because we want to use these two things together to understand the process and help make decisions. So we're going to take a second and look at how charge itself is being measured by these two devices, because you're going to see milliliters, millivolts. There's lots of information coming out. And as folks in the lab or folks in the machine, it's really important to know what the outputs mean relative to the changes you want to make. And it's really driven by how the charge is measured. It's one of the reasons there's an inline version of one test and not the other, is over time, how you're measuring it is a factor. So the way it's measured is like this. So picture this as a jar of water. You can see loose charges around. The pink positives or the pink anionic negative charges and the gray cationic positives are floating around in the water. And we put in a charged particle. We have a small dissolved piece of anionic stuff with negative charges all over its surface. Now, as it's floating around in water, positive, the gray cationic ions will gather around it. Now, they're not neutralizing it, they're just being attracted, they're getting near it. The way the measurement is made is by displacing those ions and basically moving something nearby it to kind of brush the gathered positive ions away from that negative surface. And when that happens, you create a streaming potential, a voltage. You have a charge differential between the ions that moved away and the ions that were left behind. And you see that in millivolts, a voltage, a potential. When you first put your sample into the Mutec, the PCD, and the plunger starts going up and down, it is displacing the water. It is moving those ions up and down, and you get an initial millivolt reading. And what it's doing is it's creating a measurement that understands how many of the positive ions were gathered near the particle. And that is an indicator at first, maybe, of how the strength is. What you do at this point is then you neutralize the charges on the particle, and that number will get smaller because less ions will be gathered around. So the first number that you see on the Mutec is streaming potential in millivolts, but that's not the reported number. That's just an understanding of what you're starting to see and what it's looking at. It is starting to understand what the charge of those water particles are by moving the ions next to it. So how is it making its measurement? It's doing a titration. In the old days, you'd have two pipettes and you'd squeeze a little in and the number would bounce and get closer and closer to zero. You are going to add that material into the sample. In this case, if it's an anionic particle, you're going to add a cationic, oppositely charged titrant. And when the titrant goes in, it will actually neutralize the charge on the surface of that particle. As it does that, fewer and fewer ions in the water, those positive gray ones that kind of were just coming over to see what was going on, fewer and fewer of them are coming by. The streaming potential starts going towards zero. And eventually, when it's completely neutralized, all the onlooking ions are gone, and it will read 0 millivolts. The charge on that particle is completely neutralized, and all the bystanding and the rubbernecking ions are gone. It no longer measures a streaming potential. The consumption of the titrant in milliliters that it took to get to that point is the reported value. And that's how you're getting your output from the water phase and the particle charge detector in milliliters. How many milliliters of titrant did it take to neutralize that material? Wonderful, straightforward, highly valuable. And if you notice, the titrator on the new one is integrated. You push a button, it does all the titrating on its own, and you kind of are refilling the titrant almost like a printer cartridge, and off you go. It's not cumbersome. You're not making things down. You're not manually running pipettes and trying to read meniscuses. Great way to get information quickly and repeatably on the desktop with the particle charge detector, the Mutec. The SZP, the system zeta potential, is using the same setup to generate its information. It is using the movement of water past a surface to create a potential. But instead of moving by a small particle and measuring it in that scale, we want to look at the fibers. So on the left, you'll see a little, basically a straw, a big straw going down in your sample, and we'll pull vacuum at the top and it draws material up into that container in the middle. And you see a representation of it on the right. As it starts to fill up, there's a screen inside, and the fibers from your sample start to build a mat on the screen. And as the liquid is pulling up through, the vacuum on top knows when that liquid and mat are at the right vacuum that you want. You can set that. And all of a sudden, the vacuum will pulse and the liquid starts going up through the fiber mat and down through the fiber mat and up and down and up and down. And you're simulating the same thing you're doing with the Teflon plunger and the PCD. You're creating movement next to the surface of the fiber, and it's looking at the group of ions that have gathered around the surface. And as they move up and down, it's measuring that potential. That is how the zeta potential reading is given, and it's given in millivolts. The way the information is created is the same. The difference is it's not as discrete as the Mutec PCD because you're not now titrating the fiber surface. You're looking at that millivolt reading. The benefit for the process is you get a really good idea of how the fiber surface looks now. And if you put in an additive, you'll see exactly what it looks like after. The zeta potential for the fiber, because it's being driven by the vacuum, is got some flex to it by the amount of vacuum you're adding. The conductivity of the water that's going up and down past the fiber also has a contribution. So you can add different conductivity values. Those things are part of the calculation that's creating the fiber charge. The number of ions and conductivity in the water that are standing around looking at the fiber are different depending on how many are available in the first place. And that allows a zeta potential to be calculated. But we're still calling it a relative value because, you know, there's not a titration or a final amount. That would take a long, long time, and with fibers and fiber surfaces, it would be highly variable to do. The value we get from the potentiometer is excellent. And the best way to use it is to look at it before and after an additive dosage. So here you see a fiber that's been put into the zeta potential, the SZP before an additive, and it's giving us a potential reading of negative 14.8, kind of the anionic or negative footprint of available charged positions. If we go add cationic additives to it and then remeasure it, we can learn a lot about where the additives went and how effectively they went on the fiber by running it again. When those additives go on the fiber, we will see a change in the zeta potential resultant from the use of cationic materials adhering to and basically neutralizing a lot of those anionic positions. And the difference between those two numbers before and after an additive really help us understand did the additive go on the fibers. That's excellent information when you're reviewing your system and mapping it from back to front across where your additives run. Now, I just used the term mapping your process, and that's really the most beneficial way to get information on the benchtop. And the effectiveness of doing it with both the fiber charge with the SCP, the system zeta potential, combined with the Mutec PCD water charge has a fascinating focus on how effective your additives are. Are they getting on the fiber or are they getting in the water? What is my charge operating window? Those things will become clear when we start using the two charge approach. Because when you put in an additive, there's more than just the fibers that are available in the water. There's our good friend, the anionic thing, the particulate dissolved in the water. We call it anionic trash because it's really not useful and it's kind of junk, but it has high surface area and can be very detrimental to the use of your functional additives and can really consume pound after pound of them to neutralize the charge, preventing it from doing what it's doing. Because when the additive goes in, it has a choice, fibers or trash. And we really don't want them to go onto the anionic trash. If we do our analyses, we can understand the values of both the fiber charge with the SCP and the anionic trash with the PCD, and we can come up with an approach to use a high charge density, lower cost fixing agent. We can neutralize the anionic trash with a material that's designed for that. So that when we bring the additives in, they have a much more clear path to go onto the fibers. And when they get over there, they can get in the sheet and they can do their job. And you can run at lower dosages because you're not wasting those fabulous blue additives over on the right with the anionic trash. And that is the first step in dealing with some of the challenges, the charge window understanding, and the rest of it is information from these lab tests. So both of these charges are measured as part of the review because we can get information on one from one tester and the other from the other. The reason you see in practice a lot more of the result on the right is after you've done your review for the zeta charge and you know which additives are being effective, the impact of the water, what you really start looking for are changes in the water side that indicate your additive is no longer going on the fiber, but also going in the water. So in practice, and we'll talk about this a little later for control, you don't always need both. But when you're doing your initial mapping and information creation to make your pathway of how to deal with your problems, both of these bits of information side by side are critical to understanding the picture. And so if you put in an additive in your process and you measure the fiber and charge beforehand and you measure them again afterwards, you will see changes in both the fiber charge and the water phase. And by observing those changes, you can understand if the fiber charge before and after showed a change that reflects the additive adhering to the fiber, it's visible. If the water charge changes before and after in a way that looks like the additive went there, it's visible. If the fiber charge is moving more than the water charge, probably getting more in the fiber. Water charge moving more than the fiber charge, maybe you're not getting it where you want to. And you can start making some hard decisions about dosage order, points, type of chemistry, and really unlock the path forward. Highly valuable information from both of these devices. And with that in mind, what we'd like to do now is go over to a demo and have Manfred show you how to actually run these devices, because getting this highly valuable information is pretty straightforward and sometimes kind of fun. So Manfred, would you show everybody what it looks like to get that information?
With pleasure, Todd. Thank you. And greetings to everyone from BTG in Germany. Let me first remind you if you have any questions on today's content or any questions you always had but never dared to ask, type these questions into the Q&A section of the webinar. So, and for the next 10 minutes, this will be our playground here. I've set up for you an SCP-10 to measure the fiber charge, a PCD06 to measure the dissolved charge. We have a pulp sample here, and we have a cationic fixative. And what I'm going to do is to dose this fixative into the pulp suspension and then draw conclusions. We will be using measurements, charge measurements, in order to judge whether our fixative dosage was successful or not. So before we can make such a judgment, we should know the initial charge values of our pulp suspension. And in order to save us some time, I have done these measurements already prior to the webinar. So join me, please, in having a look into an Excel sheet. So, and what we got here is before the fixative dosage, measured with the PCD, a cationic demand of 0.89 milliliter. So the sample itself is anionic, means it's demanding cationic additives. Therefore, the result is called cationic demand. And this minus 0.89 is quite a significant number. And you can also name this red column here the problem of the suspension. Because as you have heard from Todd, this anionic trash, this is present in dissolved form, which makes it highly reactive. So whatever cationic additive you would be dosing into the suspension, this charge here, this will be the primary reaction partner. And if you're trying to add additives onto the fibers, so like starch or any strength resins, grease barrier chemicals, you must take into account that a portion of this fiber additive will be consumed by this anionic dissolved charge here, and that only the rest of your fiber additive will make it onto the fibers. So it is a smart thing to take care of this anionic charge here and to eliminate it by using a cationic fixative. Because once this thing here is taken care of, you are evening the ways for the fiber additives to efficiently react on the fibers. And the fibers of our pulp suspension have a Cedar potential of roughly -31 millivolt. So anionic fibers, happy and willing and ready to react with your cationic fiber additives. So follow me back, please, to our laboratory table, where I'll now dose the fixative into the suspension. So this fixative is pretty dissolved, but there is quite some amount required for our first attempt dosage. And after adding the fixative, we need a couple of seconds of a good mixing. Ja, enough for today. So, and I'm suggesting to start with a PCD measurement. For the PCD, this is measuring the dissolved charge, and dissolved charge happens in the filtrate. So we must extract a filtrate out of this pulp sample. And a very common way of doing this is using this screen beaker. Oops, here we go. Screen beaker. Push it into the suspension and let it get some filtrate into the beaker. Okay. And then what you're going to do is extract 10 milliliter. So 10 milliliter is the standardized, or I should say very common sample volume for a PCD measurement. Because when you want to communicate in cationic demand in milliliter, it requires a sample volume of exactly 10 milliliter. And I'm injecting this one into the measuring cell. And I'm starting the potential measurement. So what is happening now in the PCD, as you've heard from Todd, the piston is now stroking up and down, creating a continuous up and down flow of the liquid. And with this flowing liquid, we are shearing off counter ions around the charged particles, creating a streaming potential. And here we are measuring a streaming potential of -610 roundabout millivolt. So, and what the instrument will do now is to take note, it's a negative charge that we are measuring here. So it will take the oppositely charged polyelectrolyte from the titrant and inject it into the measuring cell until this negative streaming potential is neutralized. So, and I'm starting the process now. The PCD06 can do dynamic sorts of titration, means it has some intelligence to respond to the signal changes. If the millivolt signal after an injection would change very rapidly, for the next step, the PCD would reduce the dosage. And vice versa, if there is barely any millivolt change after titration injections, it will just speed up and increase the dosages. And we already got a first result from the PCD. And we are measuring a cationic demand of minus 0.11 milliliter. So let me enter this into the Excel file. So after fixative dosage measured with the PCD, we got a minus 0.11 milliliter. And if we look at this result now here, we started with an anionic trash load of roughly minus 0.9 milliliter. We are now, after the fixative dosage, reduced to minus 0.1 milliliter. And you could conclude now that our fixative dosage seems to be a major success because all anionic trash is gone. So obviously, we are first takers. Our first tried fixative dosage seems to be just the right one. But needless to say, we have another instrument here on our laboratory table, and we should include this one as well. And we should definitely draw only a final conclusion after we have double-checked the charge on the fibers. So, and this is what we do now. For an SZP measurement, I will first need to re-homogenize the suspension here. And suggested sample volume is 500 milliliter of the suspension. So I'm just taking 500 milliliter into this beaker. I'm placing it underneath the measuring cell. Then I'm lowering the measuring cell into the suspension, and this suction tube will now dive into the suspension. And once I start the measurement, a vacuum pump will draw the fibers into the measuring cell against the screen, where these fibers remain fixed now. So there is now happening a sequence of just applying vacuum in order to compress the fiber plug that we have formed now inside of the measuring cell. And in a couple of seconds, the unit will start oscillating the vacuum between two values. And with this oscillating vacuum, there will be a tiny liquid flow up and down. And along with this tiny liquid flow, these counter ions gathered around the fibers will be replaced again, and we are creating a streaming potential. So vacuum up and down in the SZP, pretty much similar to piston up and down on the PCD. But here optimized and dedicated to the fibers, whereas the PCD was for colloidal dissolved material. So in a couple of seconds, we will be getting the result from the SZP. And the SZP10 gives us now a minus 11.2 millivolt. Oh my gosh. So let's enter it into the Excel file again to have the complete picture here. Minus 11.2 millivolt. So, and now I must say that what looked as a super successful elimination of anionic trash on the PCD side now appears in a way different light when we include fiber charge measurement, because now it is revealed that we have strongly overdosed fixative, and that we got a lot of cationic fixative on the fibers, made the fiber charge change from minus 31 millivolt down to even minus 11 millivolt. So, and by this, we have subdued the fibers in efficiently reacting with fiber additives. So like almost 2/3 of the fiber charge, we have just in a matter of seconds demolished by this fixing agent. And this capacity is now missing for the fibers to react with fiber additives. So overdosage of fixative we have as a first learning. And now imagine that you would have done this trial in absence of an SAP fiber charge measurement. This is what we would have got. The only thing that we see with the PCD is there is a demand for fixative, and in the dissolved matter, all fixative, all anionic trash is eliminated. We wouldn't be able just to reveal that we have a severe problem on the fibers now. And it is a common misconception. The PCD will show a fixative overdosage immediately. So just wait until the PCD turns cationic, and then I will detect my fixative overdosage. Now, what the PCD does, it takes care of the dissolved charge. It can only tell you dissolved charge, charge eliminated, check. What it cannot show is charge on the fibers. So what would happen if we would even further overdose this cationic fixative? The fibers, they are still available as reaction partners, still anionic. At a certain point, they will be turning cationic, strongly cationic. Only if the fibers, the overcharged cationic fibers will start even repulsing the fixing agent. Then we would be able to see free cationic fixative in the filtrate. So, having this said, I will turn back over to Todd to share his presentation with you again and explain you a little bit on how you can turn a problem found in the laboratory dimension, how you can turn it into a process solution. Todd, please take over again.
Wonderful. Manfred, I appreciate that demonstration. I know I've had you show me that several times as we've gone out in the field to help customers do the mapping. And the information that is provided is very eye-opening in almost every case. The number of light bulbs and things that get explained that were experienced and hypothesized about can either be confirmed and actions taken, or sometimes you learn something new, you come up with a new hypothesis and can move in a different direction. But the ease of use and the reliability of the information is what really drives the differential to going and being better from day to day. As Manfred outlined, you see information from this mapping on the water charge and the fiber charge. It is critical to continue to look at the fiber charge, and mostly that's done on the benchtop. On a day-to-day basis, once you've identified how you want to approach it and what you're managing, the most common way to control it is to look at the water charge. And this is a very complicated, detailed slide, so we're not going to go through it. But as you look at the additives coming from the bottom left up into the pulp chest, and then the pulp chest going towards the machine with other additives coming into play, the white water is returned back to those chests to use as dilution. When things aren't retained well, they tend to go in the water and build up over time. So as we mentioned, we're looking at things like first pass treatment, but one of the places where the water charge tends to come and get you is in the buildup over time. And what people have done in most cases is utilize charge sensors in the water phase to see what that looks like. Once the balance is made and really dialed in with the lab for both fiber and water charge, you can run those again as you go. But when you go home on Saturday night and you want to have dinner and know that the process is running well, you want to keep track of what could be sneaking up on us when we're not looking. And that's what's done with online measurements in most cases. A measurement in the middle of the screen there is made with a sensor, and I'll talk a little bit more about that in a second, but a sensor is taken that can sample both the white water, and it follow the green line over to the left, can also take a water phase sample out of a thick stock line and look at both the water loop that's coming back as well as the water phase of the stock that's coming forward. And it can be looking for issues of things that are getting into the water that could lead to foam and deposits and other issues. And it can also look for the neutralization of the trash that could lead to foam and other issues from being closer to the isoelectric point. And it really helps maintain the operating window by adjusting fixative dosage to keep it between a couple of guardrails, which you can set by doing your lab work. This is what most people do in practice once the mapping is done. So just to shed a little more light on this inline device, we call it the single point charge measurement. It's actually taking from two different spots, a single point of thick stock where we're pulling the water from, and we can also do a very low solids white water sample. This is actually the case where it's like a little German clock where we're actually doing the titration inside the device in the mill. The sample is brought in and the titrations are made with the same kind of movement that is happening on the lab desk or benchtop with the PCD. So you're getting very similar readings. This version of measuring charge in line has come a long way. Back when the PCDs were first developed, as people were going to alkaline sizing and ash, a lot of charge testing units were put into mills, particularly with bleached furnaces, and had trouble operating. There were a lot of moving parts. There was a lot of plugging. There were issues keeping reagents running. And the change from those days to here of measuring in a single point and having a nice repeatable sample brought to the analyzer has made all the difference. The use of the SPC 5500 in practice has been much higher success rate, very effective at driving balances between grease chemistries and fixatives. It's turned into a fabulous way to help balance and keep the wet end in control. But the information on where to put it and what to adjust was done in the lab with a particle charge detector and the system zeta potential. Fantastic pairing of devices. So Manfred showed you how easy those were to use. We've talked about the effectiveness of the charge, and we spend a great deal of time talking about it because it's going on every day, and the new chemistries are really pushing those kinds of observations, and that information is immediately valuable. The device over there on the right is one that sometimes doesn't get the attention it deserves because people have really moved away from doing a lot of the predictive testing they have in the past. They've tried to simplify it, just running a couple Canadian standard furnaces. People have put the Brit jars away, and you're getting very limited screening of information. A lot of times the screening is brought in by the vendor and you're taking other folks' word for it. This device is a great way to get repeatable information very quickly with reliable additive dosage and screening properties that make the comparison of information in the lab really good. So let's talk about it just for a second as we wrap up. This device can make the selection of your next step additive much easier and done with a little more confidence. In a resource limited world where you don't want to spend time doing all the screening that you probably should, and you don't have enough engineers to run the trials, this device is probably invaluable. In an afternoon, you can screen 10 different products effectively with multiple repeats and multiple dosages and really get good information on the dewatering, what the retention looks like, the impact of the molecular weight and charge changes you're making to the small solids that pass through. And this information can be invaluable and really starts to make adjustments at a small level where you can start comparing 10 and then pick the two best and really put those under some strain and pick the better of those two. The device is easy to run, and it increases the effectiveness of one person working from 3 or 4 samples per hour to 20 plus samples in an hour. You can create a lot of information very quickly. You put the sample in, it's got its own stirrer, the RPMs, the amount of time that it's stirring is set. The additives are being put in through pipettes in the timing that you choose and the order that you choose. You can evaluate what is being done position to position very quickly. You can look at the order of addition very quickly. We've got the screen options. We have a sensor out the bottom to look at the solids that are coming through, and the drainage rate is done across things where you're weighing things to the balance. So you can look at the speed of drainage, how long it takes to go to get the material out. You get more than just the time. You get a great deal of information to help discern the difference between a couple different additives that you're using. Looks a lot like a paper mill at a real small level, and I know a lot of folks over time have said that about their devices. The benefit of this is it sits on a 10 by 10 inch square on your desk, on your benchtop, and can create a ton of information around additive dosage. It used to take me all morning to set up a Brit jar, all afternoon to set the base load and get samples, and then day 2 was spent getting a handful of okay information. By the time I was at lunch on the first day, you probably have done more work than I did in the entire week. And if you work on it that afternoon, you can look at various permutations of additive orders and the rest of the types of things very easily with the system set up for the additive dosing. The shear under the forming conditions can be adjusted. It is much better to create a flow through of material that allows for retention measuring and drainage rate review than standard work on the freeness or the Brit jar where everything just runs through. You've got a significant ability to learn how these additives interact. And as we said at the beginning, the interaction of the additives drives the efficiency and the effectiveness of those additive dosings. And you're able to see it here before you use it in the process. That invaluable understanding before you take it out on the machine floor. The information comes out, it's digital, you're not writing it down on a log sheet that gets lost. You can quickly plot, you can quickly compare, and move ahead with the information that you've spent a lot of time generating in the lab. And the grainy old picture on the right is just perfect, because I think I found one of these in a lab that I'm not sure anybody had been in a while the other day. We sort of got it running. And after we did, we're looking around and said they really could use a DFR in here, because this mill is moving ahead with all kinds of advanced measurement around controlling refining levels, controlling charge and strength additives. Wouldn't it be nice to know what we think we're going to expect to retention, to drainage rate when we switch over to this chemistry? This benchtop device can really increase that amount of information very quickly and easily, and reopen a stream of information that kind of went away when lab resources went away. You don't need a lot of people to get a ton of information in this area anymore, and this can be a super return on investment to help save tons when it's trial time or vendor changing time. What are these new chemistries going to do? So as we pull to the conclusion, I'm going to hand it back to Peter here in a second, and he'll kind of share some information and look for questions. But the key to this is the interaction of the materials you're using is critical. And if you don't know what's going on because you're not measuring it, you're flying blind. You're making adjustments. You have to wait 30 minutes and maybe losing paper while you're waiting to see what happened. Measuring it brings your response time down to seconds from now. What did this do? And if you work on some of the prediction, is it following what I expected to happen? Can I add more? Can I carry on? Or am I seeing something I don't like? Should I make a different choice? Measurement opens the door to understanding what is going on so you make better decisions. And when you're making the better decisions, it's a lot easier to optimize costs, uptime, and other issues that come up like deposits and dosage. Those avenues are unlocked with the measuring. And so, Peter, as I kind of go over here to the conclusion slide, I just leave everybody with this: is these types of things had been done for a long time in the industry and had a lot of value, but had some challenges. The new smart technologies and the limited resourcing available has made the environment to kind of re-energize the use of these devices in your site perfect from a timing perspective. We're happy to take questions and connect as best we can, because we see a lot of value for the sites that want to move forward here. Peter, take it away, close us out, and see if folks have any questions.
Thanks, Todd. Thanks, Manfred. For sure, we had a short time slot, and you brought up a lot of points and a lot of content, and for sure we can go deeper if there is more time available, or separately when you get in touch with us. I have seen some questions coming in, and the first one is a very easy one, which is more administrative, and I can answer directly. Will this presentation be available online or for download? And the answer is yes, it will be for all registered people at the session here. They will get an email as a follow-up with a download link for the presentation. Other questions coming in is, I have a first one, I think, for Todd here. Can we check charge for chemicals like OBA or AKT?
That's a great question. And part of what I would say is I have seen that type of desire. And talking to Manfred, I may actually ask him a question here in a second, because the biggest concern that's always coming across my plate when people want to add high charge density material directly into the PCD is, how do we clean it back out? Because I think we made the case earlier for the fact that the device wants to be clean to run. So I would say, Manfred, is there a protocol for looking at additives and devices for the operation of the machine to do the titrations, and also make sure we have the right amount of titrant and can clean it and use it for other things afterwards?
Todd, indeed, there is a protocol for the cleaning in place, and it involves some chemistry also, some detergent, some acetone, and a salt is mixed into this cleaning recipe as well, making this our, let's say, bread and butter cleaning solution. It does clean a lot, including, like you mentioned, residual polymers that you have done from such a chemistry test. And even more important, besides chemical solving, is mechanical cleaning. So by using a piston brush and really rubbing the surfaces, the inner surfaces of the measuring cell clean.
Yeah, so Peter, I guess in a nutshell, what I would say is, as long as the titrant and the material being used is prepared properly and cleaned properly afterwards, that is something that the device will do, is it will look for that settled point in the middle. But I would recommend folks reaching out and contacting us when they're looking for that type of evaluation. I think there's an opportunity for things to happen to the PCB that would make it less effective down the road. But with some simple setup, I think we could help get the results those folks are looking for, and also keep their device healthy enough to continue carrying forward testing after that.
Okay, thank you, Todd. I would say, Manfred, you touched it already, but maybe you can one more precise answer: how to clean the equipment if there is scale on the bottom of the PCD tester.
Mm-hmm. There you can, if the acetone cleaning solution that we spoke about before cannot dissolve the scaling that you see on the bottom of the PCD measuring cell, then the good news is the material is PTFE and the electrodes are made of platinum iridium. So you can use also aggressive chemicals, namely, for example, sulfuric acid. You can go up in dense up to 70%. So fill it in the measuring cell, let it work a couple of minutes, and then you will get a perfectly white measuring cell back. Handling with such aggressive chemicals needless to say, but I'd love to mention this. Take care. So do it in the, in a ventilated environment, and wear all protection equipment that you have in place.
Good. Thank you, Manfred. I have one more for Todd, maybe, or Manfred, but I would say I hand it to Todd first. Does the DFR have vacuum shear?
Peter, would you repeat that for me?
Does the DFR have vacuum shear?
Vacuum shear. That's a good question, Manfred. I know that there's shear created with the propeller blades, and I believe they'd probably be looking for a pulsing type vacuum shear that's been used to simulate foil boxes. Maybe you can talk about some of the available options, because those things can be valuable.
A vacuum we have not available in the DFR. So what we do have is free gravimetrical dewatering, and we have press disk dewatering. So, and the press disk dewatering you can use to simulate press dewatering systems like chamber filter presses or screw presses. But indeed, there is no vacuum coming with the DFR. Yeah.
So the shear is coming for the mixing, for the drainage that would look at the fournier.
The shear,
the ability to look at pressing to simulate the presses there, which is very effective also. Perfect.
The shear forces really to stress the flocks that we have that have been created by the polymers. This is purely coming from a stirrer, from a mechanical stirrer.
Perfect.
Good. It looks like by that we have answered all of the questions. Nevertheless, for those who have put their name there and which need a deeper clarification or explanation, we will get in touch with you. Hope this is okay. Other like that, it's just for me to say thank you to Todd and thank you to Manfred for preparing all the presentation material and doing here a nice presentation and explanation of the functionality and the usage of our laboratory equipment. And I say thank you to you in the audience for taking the time to listen to the two of them here. And I want to remind you, don't forget, let's keep in touch. And there is a number of ways to keep in touch with us via LinkedIn, via YouTube, via our homepage, or also via Twitter. So use whatever is your preferred channel to get in touch with your local BTG lab or other BTG related contacts. By saying that, I want to say again, thank you to everyone, and have a nice remaining midsummer evening.